Hi, my name is Manish Gupta, and in this video, I'm going to talk about OpenAI Glide, which is for photorealistic image generation and editing with text-guided diffusion models. So let's get started. In this video, this is the agenda. I'm going to talk about, going to do a recap of diffusion models, specifically DDPMs. We'll talk about architectural improvements to DDPMs. I'll also talk about classifier guidance and then classifier-free guidance, and then talk about various aspects of Glide. How is Glide trained? How can Glide be used, and so on. Why is Glide important, and so on. Glide has been super important. In fact, DALL-E, as you know, has been very popular for image generation. However, Glide is a particular model which has been the first model in some ways which could actually take your first diffusion model, which could take text and then generate images. Okay. DALL-E has not been a diffusion model. So therefore, in Glide, people wanted to extend the existing DDPM to become text conditional. And that is why Glide is a very important bridge so as to understand how to use diffusion models for text conditional image generation. This particular video is quite mathematical in nature. So it would be nice if you actually look at earlier previous videos that I've recorded. So on DDPM, clip, and DALL-E. So those videos will sort of some of those concepts I'll use in this video. Okay. So we'll get started. So what are DDPMs, right? DDPMs, the full form is Denoising Diffusion Probabilistic Models. Well, these models were proposed in this paper, and the model actually uses this kind of a method so as to generate images. It starts from a noisy Gaussian thing. So it starts from there. We call it basically XT, and following the reverse process by doing multiple Gaussian transitions, it actually leads to an image. So it starts with noise, and then over time, as you see, it sort of improves in the image quality, and finally it leads to a very reasonable image. Okay. It is not text conditional. It is basically just starting from noise and then essentially leads to a good image. Okay. The good image we are going to call as X0, and then the noisy image we are going to call it XP, and then there are several different levels of noise which are there in the transition steps in between. Okay, the reverse process is the process of taking noise and then creating the image, while the forward process is basically the process where you take the original image X0 and then get the noised version. Okay, so that's that. Now, so X0 is sort of sampled from the data, training data, X1 and X2. So all of these variants of the image with noise are essentially of the same dimensionality as the original image. Reverse process is therefore then a Markov chain with learned diagonal Gaussian transitions. So these Gaussians are spatial. They are also diagonal in nature, which means the variance is basically an identity matrix. Uh, and yeah, so that's that, right? That's that. In fact, the reverse process is actually given by P, where we are trying to essentially get the noise, add more and more noise until it basically becomes total white noise. Okay. So that's that. So the reverse process is parameterized by some parameters theta, and we'll talk about what is the model to learn those theta. But and it also comprises of these Gaussian transitions. So the Gaussian transitions follow a mean and a standard deviation, and they are the ones that are actually decided by theta. And we'll talk about how they are decided in the next slide. Okay. The forward diffusion process is actually simplified a lot. So it also, of course, involves several transitions, Gaussian transitions. But then here, the Gaussian transitions are parameterized like that. In fact, they have the mean and the variance actually depend on betas. They also follow diagonal Gaussian transitions. They're parameterized by betas. And interestingly, in this paper, the authors decided to fix betas to constants. So for the forward process, at least, the betas have been fixed to constants, beta 1 to beta t. And therefore, the forward process Q has actually no learnable parameters. There is no learning involved as such in Q, right? Um, now, if I define alpha as 1 minus beta, and I can sort of define the cumulative alpha as alpha bar in that senses, so that's a good notation to remember. We'll use that later. Okay. Now, how about the reverse process? So the forward process has no parameters to train, but how about the reverse process? The reverse process actually, of course, also has a variance in mean, as you see. So variance sigma and mean mu. So in the reverse process, the variance is actually again set to a constant. So essentially, you can call it sigma square, or well, it is set to beta t. So the variance is also set to a constant, and as you say, as you see, it is beta ti, which basically means it's a diagonal Gaussian. Yeah. The mean, however, is set to this value. Now, there is, of course, proof in the paper, and I'll not go into that mathematical details, but the idea is that mean is actually set to this value. It is estimated using a model called epsilon theta, right, which is parameterized by theta. So 1 over square root of alpha t xt. So xt is the actual image, and the idea is that, or rather, xt is the image at the time point t. And what you want to do is to basically use the forward process to generate xt minus 1. So the way you would do that is by basically using this diagonal transition. But the way you would do transition, the mean that is used is basically dependent, is actually calculated by using this formula. Now, what is epsilon theta? Epsilon theta is like the kind of noise that you add. So it is an estimate of the noise to be added, to be added so as to essentially do the forward process. Remember, forward process to do the reverse process. Sorry. So remember, the reverse process essentially goes from x0 to xt. So you are continuously adding noise. So the way you add noise is you basically take xt, you add some noise, and then that gives you your xt. That gives you the mean using which you compute xt minus 1. Now, how are these parameters theta learned, right? They are learned by actually minimizing the variational lower bound on negative log likelihood. Okay, so this the way the training is performed is the process called variational inference. I'll again not go into details of mathematical details of variational inference, but the idea very intuitively is as follows. While you're doing forward process, we denote forward process by Q. While you're doing reverse process, we denote it by P. So what you want to do is to align P and Q as much as you can, right? Think of it that way, right? And that is what is going on in this estimate, lower bound estimate of the negative log likelihood. So for given data points, what you want to ensure is that for any particular data point which is sampled from the actual training data queue, right? What do you want to ensure? You want to ensure that at every time point, at every transition point from 1 to capital T, the images should be aligned as much as possible. So P of xt should be as close to Q of xt given x0 as much as possible. Remember, you have x0 because data is what is given to you, right? So therefore, when you generate, let's say, the noised version x capital T, it should be as close to P of xt as possible. Similarly, if you take any time point t, you want to observe that the image at that time point, p and q, both of them are as close to each other as possible. Okay. Lastly, when you have so this is the generation probability of x0 from x1. Now that's special. Why? Because images are discrete in nature, right? So essentially, Gaussians are continuous, but images are discrete in nature. They have 256 bins, and therefore there's also this term which can be called as discrete log likelihood, which is sort of required when you're trying to compute the log likelihood of your labeled of your existing training data. Okay. So overall, to be able to learn these epsilon theta, what you want to do is to minimize this particular quantity, which is essentially variational lower bound on the negative log likelihood. I've copy pasted that one here. Okay. Now, if you look at it, interestingly, this part, this part which is called as LT, this part essentially is going to be a constant. Why? Well, remember the forward process, the variances are constant. So if forward process variance are constant, there is no learnable thing in Q. And there's no learnable thing in Q, well, these are all constant. So this particular part is constant, and therefore the KL divergence is constant. Hey, by the way, yeah, DKL is the KL divergence. So you have two distributions, Q and P, and you want to make sure that the KL divergence is as small as possible, right? So since LT is since Q is has no learnable parameters, well, therefore the entire term and the KL divergence is constant, and therefore we can ignore that. Okay. Therefore, what we want to minimize is the expectation for these two terms, right? Now, for these two terms, if you look at the second term, it is a sum over various time points, and let's look at one particular time point t minus 1. Okay. Now, again, there's a whole bunch of derivation in the paper, which basically derives that, hey, this is going to be that quantity. The KL divergence can be computed like that. Okay. In fact, broadly, intuitively, what it says is that if epsilon is the actual noise, then what I want to do is to predict, epsilon theta is the predicted noise. Okay. So I want to take the original image, right? I want to take the original image x0. And well, I have already added noise across t different time points. So I take that. And then I essentially take the original's epsilon, which should ideally be, a white Gaussian in that sense. So on one, and I interpolate between that. So I take basically my x0, I take my epsilon, which is basically two extremes in that senses, right? Uh, I mean, if this t is the first time point, then it's a white noise. Otherwise, it's basically epsilon as you would observe in the, as you expect to observe, right? So you have epsilon, you have x0, and what you want to do is to ensure that you can take this image, which is basically formed by using x0 and epsilon, a combination of that, not a linear combination, but a weighted combination of that, and then use epsilon theta to predict an error image as close to epsilon as possible, as close to epsilon as possible. That is how you basically train train the theta in your epsilon theta model. Okay. So that's your LT minus one, and you can compute all of those LTs like that. Now, the last thing that you're left with is L0. Now, as I mentioned, what is L0? It is the probability of the image given x1, and it's a discrete log likelihood. So again, you assume that your image basically contains 255, each pixel contains 255 unique values. So you have to discretize the value to the closest bin, right? I'll not go into these math formula, but this is a very simple way of understanding what is L0. Each color component is sort of divided into 256 bins, and you compute the probability of p theta, of x0 given x1 landing in the correct bin. So essentially, you compute the probability. What is the probability that will land in the correct bin? Okay. So essentially, for the Gaussian, you essentially do area under the curve computation, and that is why you see this integral sign here for the bin boundary, bin range, effectively scaled linearly to -1 to 1. Okay. That's that. So overall, it's quite a complicated process, DDPM, right? So DDPM essentially involves, computing, minimizing this variational lower bound, right? Which comprises of these three different terms, right? And as we saw, the way these guys formulate, because of the constant variances, this term becomes zero anyway, or the constant anyway, and you need to minimize this. Is all that complicated math required? So in this paper, the DDPM paper, these folks figured out that, well, this complex math is actually not required. What they figured out is that you do not need to really minimize this, but you can actually minimize a much simpler function, okay? Where what you have done is to essentially fold in this L0 term also using Gaussian estimates into this entire term itself. And as you see, rather than actually computing this scale divergence, what you're ensuring is that you minimize the mean squared error in the prediction of the epsilons, the noise to be added at this particular time point. Okay. So you do it across all time points. So you're computing expectation over t, x naught, and epsilon. So x naught comes from q, your training data. T is from 1 to capital T. You fix a number of time points for which you are going to do this, right? And epsilon is different epsilons that can be sampled from Gaussians. Yeah. So that is that. So basically, the DDPM paper basically said that, well, you can actually generate images from noise practically by following diagonal Gaussian transitions. Yeah, and for that, they basically give a way to train your epsilon theta model. In fact, their epsilon theta model is nothing but a unit. So essentially, they say that, hey, I have a particular image and I want a noised version, right? And how do I do that? Well, using a unit model. Okay. So epsilon theta is modeled using unit. Okay. They don't have any text conditional behavior here. Note that, right? And they have made sure that their Gaussian transitions are diagonal in nature. In fact, for one of those processes, in fact they have also ensured that their variances are constant for both the processes, forward as well as backward processes, right? And the mean for the reverse process is what they are trying to estimate. Okay. Rather than estimating the mean, in fact, what they do is to essentially estimate the error to be added. Yeah, so that's that. So the training procedure essentially looks like this. You sample an image from your training data, and then you sample a time point. So yes, I mean the current time point is 0, and you want to go into time 0, 1, 2 up to capital T. You can go anywhere. So let's say fifth time point, right? And then you sample error. So from a unit from a unit Gaussian, multidimensional Gaussian, diagonal multidimensional Gaussian. Yeah. And then you take a gradient step. So the way you sort of optimize is randomly initialize your thetas, and then you take a gradient step, which tries to minimize the mean squared error in terms of predicting the error, in terms of predicting the noise to be added. Yeah, that's that. Now, uh, these models were great. Okay, however, these diffusion models lagged behind GANs. So people have been using GANs also to sort of generate images, and folks found that diffusion models are not as good as GANs. Especially for difficult generation data sets like ELSON and ImageNet. Okay. GANs, in fact, held state of the art on most image generation tasks before this new paper came in 2021. Right? But then GANs have a problem. Maybe GANs are okay. Maybe diffusion models is not what people need. But then GANs have a problem. They're difficult to scale and apply to new domains. Okay. And that is why people actually started thinking about improvement to these diffusion models so as to make them better than GANs, right? And that is what actually has led to Glide and then finally to DALL-E 2, as we know, right? So let's go step by step. Let's sort of try to understand how do you improve diffusion models so as to become at least somewhat better than GANs. And then over time, we will sort of learn how we can make them even better to make them Glide, and then further even better to make them DALL-E 2, which you and I both love. Yeah. So in DDPMs, people actually had fixed variance to a constant, as we just talked about, right? And then these folks said that, hey, fixing it to a constant is not a great idea. Don't fix it to beta t. However, rather fix it to an interpolated value between beta t and beta t tilde. Okay, beta t tilde is a cumulative beta t in some ways. Okay, so that's that. Um, now, this combination is actually decided by a neural network V. So V is a small little neural network which essentially decides, hey, what should be the importance that I should give to beta t versus beta t tilde. Okay. In this way, this is actually, rather than fixing it to a constant, it is actually a non-constant value that you have, right? That is one thing. The second thing that people do is rather than now that this is not constant, people also wanted to figure out if the simple learning objective was better, the mean squared error learning objective, which we talked about here, or do you also need this variational lower bound based objective? Okay. So people figured out that, well, a combination works better. So it is better to do a linear weighted combination of L simple plus lambda times LVLB. Well, it's not linear weighted, so lambda, very small values of lambda are also good. But then, well, you do need that small combination with variational lower bounds so as to make it robust model. Okay. The other architectural improvements to the DDPM model were as follows. They still follow the unit architecture. However, there are several changes. One is you increase depth versus width, holding the model size relatively constant. So you have more depth and less width. You increase the attention heads. So a unit model, it could also have attention heads, and they increase the number of attention heads. So use attention at 32, 1668, 8 resolutions rather than only 1616. Okay. And they also changed the residual blocks. So rather than using standard residual blocks, you could use these residual blocks. This is a upsampling residual blocks. This is a downsampling residual block. Remember, UNet is a downsampling and upsampling model. So for downsampling, you use this kind of a residual block, which basically involves ReLU 3x3, ReLU 3x3, and a pooling. And then on the residual connection, it involves a 1x1 conv and a pool, right? So on the other hand, the upsampling block essentially is more involved. It actually also involves batch normalization and so on. It also actually accepts class conditional behavior here. So what you could also do is while upsampling, if you also know what kind of images you want to generate, let's say you want to generate dog kind of images, you could actually give the class label, an embedding of the class label as input here and concatenate while actually doing upsampling. Okay, and concatenate while doing upsampling. Okay, that's that. So these are some of the unit changes. Now they also brought in something called as adaptive group normalization layer. So now what is adaptive group normalization layer? So this layer essentially incorporates, so here is the batch norm layer, right? So the batch norm layer was replaced by adagian layer, group normalization layer. So what it does is a few things. So it incorporates time step and class embedding. So remember in Big GAN, they have essentially only included the class embedding. These guys actually include class embedding as well as timestamp embedding. So So different time steps. So essentially the model remains the same, the architecture remains the same, the epsilon theta, right? It's the same unit model, same parameters. It's just that the time step embedding is different that you pass to generate errors at different time points, right? Epsilon at different time points. Not errors, yeah, noise at different time points. Okay. So it incorporates the time step and class embedding into each residual block after a group normalization operation. And what is group normalization? By the way, group normalization means this. So group normalization means that you would take the current edge, the hidden layer output that is coming in right now, right? And then you take ys and yb. So this is ys and yb, concatenation of ys and yb, right? Which is basically a linear projection of time step and class embedding. So it basically includes the time information, the class information. You combine ys times group norm of h plus yb. Okay, now what is group norm? Of course, what is group norm? Group norm essentially is normalization using groups of channels, groups of channels. Okay, so you take an image, it has several channels, you find groups of channels, and then you normalize within each group. Okay, that's called group norm. So you take h, you apply group norm to it across, over groups of channels, and then multiply ys and then add yb. Okay. So that's that. And that is what is called as ADA-GN or adaptive group normalization, which is what they have involved into the unit architecture. This basically gives them super awesome results. So uh, they call their overall architecture with ADA-GM as ablated diffusion model, ablated diffusion model. Now, besides giving the class information here, the class information in in the ADA-GN layer, they also give class information in a spatial way, and that is what is called as classifier guidance. Okay, that is what is called as classifier guidance. Now, the model that I talked about on this slide, this particular slide, slide number 9, is essentially only ADM. So they call it ADM, right, which stands for ablated diffusion model. But then if you also have classifier guidance, it's called ADMG. Now, what is it? Classifier guidance is what we'll talk about next. Yeah, it's a very simple concept actually. So for classifier guidance, uh, the idea is to explore yet another way to use the class information. So of course, you can give it as part of the group normalization layers and so on, but there is another way of using class information. The idea is that you essentially train a classifier, a separate classifier, which basically can take any noisy image, any image in that entire Markov chain, right? And try to classify what class it belongs to, right? So you train a classifier, separate classifier on noisy images, and then use the gradients to guide the diffusion sampling process towards an arbitrary class label y. Okay. So for example, at any point, if you decided that, hey, I want to generate dogs, right? So that's your class, right? And then let's say you have a model which basically figures out what is the probability that this is a dog or not. So while generating, right, of course, you start from while sampling, you essentially start from noise, right? And then you start doing Markov transitions so as to get better image so that finally it does look like a dog. So at every time point, you're going to use this classify model so as to guide those transitions. Okay, that's the beauty, and that's so intuitive an idea, right? Uh, so you start with a diffusion model with an unconditional reverse noising process. So you essentially start with this diffusion model, and then to condition on the label y, what do? You essentially have this p theta anyway, xt given xt plus 1, which you are going to compute anyway, just like a typical DDPM. However, you also multiply the classifier probability here. So the transition that you have xt from xt plus 1 is not just going to be dependent on of the standard noise addition, but well, it will also depend on whether the classifier is able to now say that, hey, this looks more like a dog or not. Yeah, so that's that. Um, now, what does this mean? This basically means that while in standard DDPM, we used to do this. In standard DDPM, what we used to do is to start from a noise sample. And for t different steps, you are essentially going to sample Z, and you're essentially going to compute xt plus 1 as that, xt plus 1 as that, right? So xt plus 1 as that. Remember, this part only comes in because you have a non-zero variance, a non-constant variance in that sense, right? So that's that. Yeah. So this is standard DDPM. This standard DDPM. However, you want classifier guidance now. Remember, you've trained a separate classifier. To do that guidance, what you do is to essentially start by sampling xt from a standard Gaussian, just like step one here, right? However, for all of those other time points, you are essentially going to sample mu and sigma, uh, not from the standard, so the way you're going to do that is not to use the standard mu and sigma, but actually use mu plus s times sigma, and the variance and the gradients from the standard classifier model. Okay. So the idea is that you want to use the classifier model so as to guide your sampling or the generation process for images. The way you do that is to sample not from the standard mu and sigma, where the mu actually comes from your unit model, right? Uh, but you actually also align it in the direction of the classifier by taking the classifier gradients, multiplying it with variance, and multiplying it with the scaling factor called S. So how much you want to care for the classifier guidance is controlled by this scaling factor S. So that is what is called as gradient scale S, right? So if you did not have that, your formula would, if you didn't have classifier guidance, your formula would look like that. Just need to sample from mu sigma. Okay. So that's that. Now, people tried different scaling classifier scaling values. So if you have s equal to 1, people observed that you did not get good images. In fact, if you increased s from s equal to 1 to some higher values, right? Like for example, classifier scale 10 here, you would get much better images. And that is why people actually use larger values of s. Okay? In fact, as you see here as well, larger values of S typically give you lower FID. Lower FID is better. FID is a distance measure to figure out the quality of images. So yes, generate images. So lower FID is better. And as you see, higher scale at least gave you a better FID in this case. Okay. Um, Now, like you were doing P of X modeling, you could also do P of X given Y modeling. So the idea is that, remember, we were actually, so far we basically said we don't have the class label at all. We're just generating images. So that's that. So while you were doing the P of X and all of those derivation, you could do the same thing with the class conditional in a class conditional way also. Okay. So the idea is if class information is available, essentially you pass it as the class embedding, it becomes like class conditional in that sense, right? So you could do class conditional or you may not do class conditional. So lower one is when you do class conditional, you pass the information to the residual layer, right? Through normalization, add a GN layer, right? And you may or may not give guidance. So if you give guidance, in fact, it turns out that 4.59. So it turns out you get best results when guiding a conditional model further. When guiding a conditional model further. So the more you use the class information, the better the results that you get. Okay. But one thing that people realized is that larger scaling factor values lead to lower diversity. Okay. It improves the quality of images, sure, but it reduces diversity. Now that's a problem that people wanted to solve. How do you solve this problem? Therefore, in yet another paper, people came up with this thing called as classifier-free guidance. So they said that yes, classifier guidance was great. It gave you better quality images, but I don't want classifiers. I want classifier-free guidance. And why and how does that work, right? So classifier guidance needs an extra trained classifier, right? You remember, you have to train a separate classifier, and that too you have to train it on noisy data also, so that it can classify noisy samples appropriately. Okay, so therefore you can't even use pre-trained classifiers for training that extra, classifier which detects the class label, yeah, or predict the class label. Now, so therefore the idea was, and that led to higher scale values actually led to poor diversity, and that is why people said, can I do a classifier free guidance? Okay, so uh, can I do that without a classifier? So the idea that people came up with is this: rather than sampling in the direction of the gradient of an image classifier, how about I actually use the same model, okay, and mix the score estimates of a conditional diffusion model and an unconditional diffusion model. So imagine two different models again, right? But they are not classifier and a diffusion model. Both of them are diffusion models. One is conditional, one is unconditional. Okay, both of them are, one is conditional, one is unconditional. Okay, yeah. So you train the two together. In fact, as we will see, you don't have two models. In fact, we will see soon that you can do the same thing using a single model. But for the sake of understanding, right, think of two models, and then you're going to mix the scores of these two. Okay, so imagine having a model which basically predicts the epsilon in a class conditional manner, and the one which predicts epsilon in non-class conditional manner, and you combine the two using some sort of a weighing factor. Okay, so rather than using classifier guidance as here, you are essentially not going to depend on another classifier, but going to just mix the probabilities or mix the score estimates from the two conditional and unconditional models. Okay. Now, how do you combine them? What is W? Well, that can be trained. That can be tuned using hyperparameters. So using validation data. Yeah. So the interesting idea is that they don't train two different models. They actually use a single neural network. Okay. For conditional, well, you pass the class embedding anyway. For unconditional model, you actually set the class embedding to a null token. That's it. Yeah. And therefore make the model learn both a conditional way of generating stuff and a class unconditional way of generating stuff. Okay, that's that. You jointly train the conditional and the non-conditional unconditional model by randomly setting C to phi with some particular probability. We will see the training algorithm also in the next slide. But that's that. What people observed is this classifier-free guidance actually gives you better quality, fewer diffusion steps. And as we will see later, it is something that contributed significantly to glide. It can contribute significantly to glide and text conditioning as well. Yeah. So now with all this mathematical background, let's talk about glide. Glide essentially is guided language to image diffusion for generation and editing. So that's the model. As you see, glide is text conditional now. So now you don't just generate random images, but you can actually say what image you want to generate. So a hedgehog using a calculator, or a painting of a fox in style of Starry Night, or a stained glass window of a panda eating bamboo. Yeah. It's a diffusion model for text conditional image synthesis. Unlike DALL-E, it actually uses diffusion, and it is for text conditional image synthesis. It compares two different guidance strategies. So we have talked about classifier guidance, classifier-free guidance. Well, people know that classifier-free guidance is better, so they also propose something called as clip guidance, and they try to compare clip is better or classifier-free guidance is better. Okay. Classifier-free guidance actually was preferred by human evaluators on good image quality metrics like photorealism and caption similarity. In fact, the images that you see here, they also show realistic shadows and reflections, high quality textures, and different styles. You can generate in different styles as well. Okay. The model is a 3.5 billion parameter model with the classifier-free guidance, and then compared to DALL-E, it fares better compared to even when DALL-E actually uses the expensive clip re-ranking. So remember, the DALL-E model actually at the end uses clip re-rankings to choose the right image. So even then, Glide is better. Glide can also be fine-tuned for another interesting use case called as image inpainting, which I'll talk about towards the end. And it's a very, very powerful use case for text-driven image editing. Yeah, DALL-E model, a filtered DALL-E model, a smaller version of it can be found here. Yeah. So how does DALL-E work, right? So it uses clip guidance, or it can also use, of course, classifier-free guidance. So what is clip guidance? Well, remember classifier guidance? So we were basically trying to motivate the models as to generate images in the direction by considering the gradient of the classifier. Well, here also you do the same thing. The classifier is replaced by a clip classifier. That's the most important thing, and that's what is called as clip guidance. And remember, we talked about this scaling factor, which has also to be introduced. So yeah, so that's that. Now, just a quick recap of CLIP. Again, I've covered this in a previous video, but CLIP is this model, a multi-modal model in some ways, which tries to learn a joint representation of text and images, right? It does so by using contrastive loss. So it basically says that, hey, if in a batch there's a text caption and there are like 20 images, you want to compute the similarity between this text and image, all the images. However, you want to give higher score to image and text pairs which are positives, and lower scores to image and text pairs which are negative. So you want the diagonal to be as high as possible and the non-diagonal elements to be as small as possible. Okay. So the idea behind clip guidance is to replace a random classifier, any kind of classifier, with clip classifier. So you want to perturb the reverse process mean. So this is the reverse process which is going on, right? Which is basically the generation process. So you want to perturb the reverse process mean with the gradient of the dot product. So what you do is to compute the gradient, but you compute the dot product, the gradient of the dot product. What is the dot product for? F of xt and g of c, where xt is the image and c is the caption. If your caption c and the image xt, what you want to do is to essentially compute the gradient with respect to that. Okay? That's clip guidance essentially. And remember, in Glide, you want to generate images in a text conditional manner. So you have the text and you want to generate the images. So you have the current text anyway. Okay. So for Glide training, how do you train the Glide model now, right? So Glide actually has three models inside, right? Inside a big Glide model, there are three models. One is a 3.5 billion parameter text conditional diffusion model, which works at a 64 cross 64 resolution. So basically saying you pass some caption, it will give you a 64 cross 64 image. So 3.5 billion parameter model. We'll talk about details, okay? Second, Glide also has this 1.5 billion parameter text conditional upsampling diffusion model to increase the resolution from 6464 to 256 256. So the idea is that you need text conditional upsampling also. And this upsampling is based on another kind of a complete computer vision topic called as image super resolution. Yeah. And people have found that it works really well here. So you use your diffusion models to actually just generate a smaller, lower resolution thing, and then you upsample it to get a higher resolution output. Okay? And then the third model that is to be trained as part of Glide is the clip model, clearly, because you need classifier guidance from the clip model, and therefore you have to have a 64 cross 64 VITL clip model, a noised version of that, because you train it on noisy data, right? That's that. So how do you train these, right? So let's talk about them one by one. The text conditional diffusion model is trained using ADM. So the same thing that we discussed a little while back, right? Ablated diffusion model, right? And we retain all of those things, improvements to unit, non-constant variance, special residual blocks, upsampling, downsampling, add a GN layer, everything. All of those are retained here. Yeah. And to condition on the text, now there is text part. Remember, there the residual layers were conditioned only on the class label and the time, right? Of course, you want to do that anyway, but rather than the class label, here you have text to condition on. Now it gives you a control key in some ways, and you can control in various ways. Tomorrow, people may actually also want to condition on speech or some other mechanism, right? So therefore, to condition on the text, we first encode it using, so text has to be encoded because you need some embedding for text to be used there, right? So you take the text piece, the text caption, encode it using transformers, right? And then the output of the transformer can be, is fed to both of these places. One, you pass it as a class embedding in the ADM layer, the ADAGN layer, and you also do this. So the last layer of the token embeddings is actually projected to the dimensionality of each attention layer throughout the ADM model. So remember, ADM model has three different attention layers: 32, 16, 16, 8 cross 8. So all of those, right? And you essentially convert the representation from the transformer. You not convert, you project it to the size of the attention layer, and you use it there also, concatenate to the attention context at each layer. Okay, so basically saying people use the learnings from the diffusion models, specifically those improvements and so on, ADM model specifically, as we can call it, and there they actually condition using the text part. Okay? So the text conditional diffusion model uses the same data set as DALL-E. Uh, the visual part has 2.3 billion parameters. The transformer part has 1.2 billion parameters. That's what makes 3.5 billion parameter model. Okay? As we discussed, this 1.5 billion upsampler guy is essentially an image super resolution model and improves the FID overall image quality. And the idea behind doing this is the usual recipe of learning a diffusion model in two stages. One is a low resolution diffusion and combined with a upsampling diffusion. Okay. During sampling, the upsampling part, the low resolution model actually produces a sample, or other, sorry, during sampling generation part, low resolution model just produces a sample, and the upsampling model actually conditions on this sample so as to generate a higher resolution, super resolution, as it is called, higher resolution version. Now you have classifier-free guidance that you want to put in, or you want to put in clip guidance. So therefore, you want to fine tune for either. And in fact, they found that classifier-free guidance actually gave them better results. So if you want to fine tune for if you want to use classifier-free guidance, you must fine tune for it. So after doing this training on the text conditional diffusion model, they fine tune it for classifier-free guidance. And the way you do that is as follows. So after the initial training run is done on the previous slide, right? You fine tune to support unconditional image generation. You don't want it to basically generate only when text is available. You want to generate it to generate images even when there is no text available, right? So similar to pre-training, which used text guidance, right? Or text labels, yeah, text captions, right? 20% of those instances actually are replaced by empty sequence. So you want to fine tune it such that 80% of the times you still pass on the text caption, 20% of the times you mask the text caption completely, right? So as to make sure that it retains the ability to generate text conditional output. At the same time, it can also generate images in an unconditional manner. Right? The other thing they also did is called image inpainting, and maybe I will talk about image inpainting and then come to fine tuning. So this is the image inpainting. Let's say there's an image of this kind, and I want to put in horses or zebras there, right? So I just select something using green color, right? Green region. And then I say that, hey, I want to put in zebras roaming in the field here. And you get, ta-da, you get this output, right? Similarly, I can do this. I basically just, highlight a part by green. And then I say a girl hugging a corgi on a pedestal. So, and then that basically replaces the dog by a corgi dog. I can say an old car in a snowy forest, and I can select the whole region also, and that gives me, it makes it snow, and it makes it snow here, right? I can actually select this region and then say man wearing a white hat, and here comes the white hat. In fact, this can be done in a sequential manner so as to create interesting designs. For example, I can add a painting, or I can add a table, or I can essentially put a flower vase on the table. I can actually move this entire sofa set closer to the wall, as you see here, Yeah. So this thing is called inpainting. So you basically human marks a green region and also provides a text, and the model fills the green region suitable to the text. While doing so, of course, the model retains the style and the lighting and inserts new object with the shadows and reflections. This can be iteratively used to create complex scenes, as you see. But this has to be, I mean, again, the model has to be fine-tuned to do this. So this is how fine-tuning for image inpainting is done. Um, you take random regions of training samples. Of course, you have to fine tune using some training label data. So you take random regions, you cover them by green, right? Remaining portions are actually fed into the model along with the masked channel. So you feed three things now: the original image, the masked image, and then also the mask channel. So that is why you augment four more channels, RGB channels for the masked image, and then a mask channel also. Okay. So that's that. Um, and then you basically do typical fine tuning so as to essentially fine tune the model for image in painting. Yeah, so that you can actually give this green labeled image and then with a caption and hope that will actually create an in painted image. Okay. Now, so that was that. People experimented with several ways of generating images with the DALL-E and with the glide with the clip guidance and glide with the classifier-free guidance. And as you see, the results that you obtain from glide are actually way better compared to DALL-E. Okay, remember this is not DALL-E 2, this is DALL-E, the original version of DALL-E, right? Which was not diffusion model based. Okay. In fact, as you see, the images from DALL-E are pretty blurred compared to the images that come from glide. That's that. You can also use Sketch with a text caption to do more controlled modifications to the image, as we discussed even on the previous slide. As you see, you can cover that and say, hey, fire in the background and so on. Okay. So let's talk about evaluation. People evaluated DALL-E, the clip guidance versus the classifier-free guidance first. So human evaluators were actually asked two questions. Questions related to photorealism. So which of them looks more realistic photo? And also questions related to caption similarity. So which of them looks like a better caption for the image, right? So images are actually obtained using clip guidance and classifier-free guidance by varying the scale, the S value, right? And as you observe on both these quality measures, photorealism and caption similarity, they found the blue line to be better, which is basically classifier-free guidance rather than the clip guidance. Okay? Although clip model has been so awesomely popular, but classifier-free guidance actually seem to be doing better. There are some numbers which also tell that, hey, people typically prefer the classifier-free guidance, both in terms of photorealism and caption-based similarity. Okay. As a standard, they also showed results on the MS Coco caption data, and they find that Glide actually performs better than any of these previously proposed models, even though this is done in a zero-shot setting. So Glide was never trained on MS Coco data, but actually performs really well, even better compared to DALL-E. Right? People also compared Glide with DALL-E in terms of photorealism and caption similarity. And what was found is across different settings, whether you do re-ranking with DALL-E or not, or you do re-ranking with DALL-E, or you essentially on purpose try to reduce the quality of Glide by blurring the images, you still observe that more people actually prefer glide compared to DALL-E. So these are how many people prefer glide. So of course, if there is no DALL-E ranking, DALL-E is a little weaker. So therefore, more people prefer glide. But even if you make glide very weak and DALL-E very strong by re-ranking, still more people prefer glide than DALL-E. Glide is not the best, and as you know, a better thing is already out, DALL-E 2, and we'll talk about that in the next video. But Glide fails, and fails in a reasonable set of cases. If you basically put up unusual requests, Glide fails. An illustration of a cat that has 8 legs, now that's unusual, or a bicycle which has continuous tracks instead of wheels, or a car with triangular wheels. Of course, it fails. Yeah. And the problem with Glide is that it takes 15 seconds to sample one image on a single 800 GPU. 800s are very good GPUs, but it takes 15 seconds, which is a little large. Okay. These are images generated by various models, DALL-E, then this is Glide, which is unguided. This is Glide, which has clip guidance, and this is Glide, which is classifier-free guidance with scale of 3. Yeah. As you observe, clearly the images that you see here are much more relevant. And this is images for, glass painting for Panda and so on. So therefore, the images, as you see here on DALL-E, the image is not that relevant. Very relevant, very sharp images, as you see there. So inpainting, here is an example of inpainting, what people can do with inpainting. So you could highlight some part of image on the leaf, and then you can just say, hey, bee is looking for food on the leaf. And well, you can actually do these kinds of things using the inpainting technology now. Right? This is pretty powerful. In fact, it could have big implications in the movie industry, in interior design. Yeah. So this is a demo made by Runway. I just found the video pretty awesome. Yeah. So in summary, let me summarize this video. So in this video, I tried to do a recap of DDPM that was quite mathematical. I do understand. I also talked about architectural improvement to DDPM. Lastly, then we talked about classify guidance, classify-free guidance, clip guidance, and then lastly, I talked about glide. In glide, so what is glide? Glide is a diffusion model for text-conditional image synthesis, and it can be fine-tuned to perform interesting tasks like image inpainting, which enables powerful text-driven image editing. Hope you liked the video. Thanks for watching.